This isn't going to be a fascinating video to watch for most people, but it's there in case anybody wants to see it. This is just a very rough video of me trying to do the calculations of the different velocities of the incoming 1 mass, the outgoing 2 mass, and the rebounding 1 mass. I was basing all this on thinking it was 25 frames per second. I think it was actually 30 frames per second, but never mind. In relative terms, that's all that counts, isn't it? Anyway, it worked out just fine, considering it's homemade Airtrack. Came out at, instead of 2/3 exactly, which would have been 0.667, etc. It was actually more like 0.64 times the velocity. And the rebounding 1 mass object, instead of 0.33 speed, it went at 0.27 times the speed. I think I already showed it that that part of the track seems a little bit suspect. It's a little bit, if the 1 mass object is going slow, it tends to stick on the track. So I wouldn't be the least bit surprised if it lost a little bit of velocity there. That's how it appeared on camera. But anyway, the most important thing I think we need to recognise is that the 2 mass object did indeed go pretty much the same as Walter Lewin showed, about 2/3 the velocity. Yeah. Okay. Just one more important point. Disappointingly, when I did it without springs, that didn't really match Walter Lewin's thingy. And I think the reason is because even though I understand why Gary compares it, metal on metal collisions to a Newton's cradle, the fact that in Newton's cradle the balls bounce very efficiently is really telling us something, that the area of contact is very, very small, really, because they are spheres, and therefore that part is highly compressible in relative terms, and therefore that is in effect a spring. The shape of the balls as they collide are distorting, obviously changing to something akin to ellipses, I suppose, and then rebounding back again. So they are effectively like springs. It isn't like a hand clap where, like a proper hard, sudden collision. It's a gradual collision. It doesn't look gradual to us, but if you could look at a microscopic level, you would see, because they're spheres contacting one another, just a very tiny surface area compressing, because it's a tiny surface area relative to the pressure, relative to the force. And therefore, it's a mistake for us to look at Newton's cradle and compare that directly with me just bashing 2 pieces of aluminium angle into one another, end on end, which isn't a gradual collision. That's a sudden collision, like that. Ball on ball collision does seem very akin to a spring collision. So I think, although I understood Gary's argument initially, when I think about it, that would explain why we don't get the same result with a Newton's cradle as we do with 2 metal on metal collisions made of aluminium angle or anything else like that. I'm sure if we put balls on the end, that would be a good idea, wouldn't it? If we put physical balls on the end of instead of actual springs, I'm sure we would still get the Walter Lewin results. I might try that. One thing at a time. Can't do everything at once. But it's good to see Gary doing experiments anyway. Okay, let's see how we go anyway. 39.27. This is the first one with springs. So we're on 39.45. 39.40. Can we not just go back on this then? 39.40. Let's go back on this. Let's go. So I count. I'm waiting until I let go. I'm also waiting until my bloody hands are out of the way. I think if we count from... I'm going to count from here, where I can see the back edge is in line with the number 2. It's just about in line with the number 2. So we count from here. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Okay. 26, 27, 28, 29, 30, 31, 32, 33, 34, 30. Oh, 4. That's 34. When it, I want to count from this frame. I want to count from this frame. I'm going to count at what time are we on? 39:49. Okay, so we got one mass, two mass, and one mass again. Okay, so let's see how many I can count of the two mass first of all. Then, okay, let's see how many I can reasonably count of the two mass. That's the way to do it. So it's on that 55 mark I said there. I can see that. Anyways, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Go back again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Now, as far as I can determine then, 25, that's a total of, let me count the inches. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. About 5.3, 5.2, 5.3, I'm going to say, is it 3 inches over 25 frame seconds. And in the meantime, let's go back and count the other one. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. If we're counting from this point, when I think I'll count the back edge of the. We're going to count from the back edge of the one mask because it's easy because it's closest. So from this point onwards, counting 20. How many frames back? As I say, 20. Yeah, 25, isn't it? Yeah. All right. Yeah, 25 frames back. So I've got to go. There's a mark on the tape, isn't there? Like a blue mark. So there's a little mark. Anyway, yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Oh, gone too far. 25 back. So the one mass has gone back. How much? I think it's currently on. Looks like 10 and a quarter. Again, 10 and a quarter, 11 and a quarter, 12 and a quarter. 2.3. I'm going to say it looks like about 2.3. It's gone back about 2.3 inches, would you say? Call it quick 2.25. Stop messing about with all these 0.3s. But what was the incoming speed? Let's have a look. The incoming speed was. So we count backwards from here. We go. So we count backwards from here. Go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Sorry, I didn't make a note of where it was, did I? Shit. Oh, of course, it's on that little pen marker, isn't it? I count from here then, don't I? I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. It's at the length of the thing itself, isn't it, really? 4 inches, 5 inches, 6 inches, 7 inches, 8.25 inches, I think. 8.25 inches. 8.25 inches. Let me check that again. 1 inch, 2 inches, 3 inches, 4 inches, 5 inches, 6 inches, 7 inches, 8 inches, and 2. Yeah, 8.25 inches. Now convert that to actual 8.25. That's stupid, wasn't it? Did I really need to do a calculation? Seeing as these are all over 1 second, why am I trying to convert these to inches per second when we know it's already inches per second? Oh, I'm a dumbass. Okay, so we already have 8.25, 5.3, and so on and so forth. So let's see. If 8.25 inches per second was the speed of the one mass coming in, then we do need the calculator, don't we now? So if it was 8.25 speed coming in, then we multiply that by 2/3. So multiply by 0.666 equals. So the outgoing speed of the two mass should have been, you have to be 2/3, should have been ideally 2 point, well, call it 5.5. 5.5. Well, it was actually 5.3, so it was just a tiny bit under, wasn't it? Now, if Gary C was correct, though, that it was only going to ever go half the speed, 8.25 divided by 2. So it's 4.125 here, 4.1, so 5.5 versus 4.1. And it was 5.3. Ah, so this actually did back up Lewin'S thingy there, didn't it, really? The one going backwards doesn't look quite fast enough, though, to be truthful. Although it did seem to lose speed going backwards, didn't it? I did notice. How many times is 2.25 going to 8.25? 8.25 divided by 2.25 equals 3. Oh, it's not a million miles away, is it? So instead of a third, it was 0.27. So yeah, 0.27 instead of 0.33 times. See, now that's not a bad result, is it, for the first one? So yeah, the 2 mass did go off at just a fraction under. What would you say? 5.3 divided by 8.25 equals. So it was 0.64 instead of 0.6. I don't think that's too bad. Yeah, so in other words, 2/3. Yeah, I think that's within